Today, we are cracking the code of matter itself. We're diving deep into chemical bonds, the invisible forces that hold literally everything together, from the salt in your shaker to the water in your body. But have you ever really thought about why they work the way they do? I mean, really, think about it. Why is it always H2O? We take it for granted, but it points to a set of rules, a deep and elegant logic running the universe. Why do atoms combine in these super specific, totally predictable ways? Well, figuring that out is exactly what we're here to do today. And here's our game plan. We're going to start with the basic forces at play, uncover a secret from a very noble group of elements, and then explore the two main ways atoms get together. Finally, we'll see how those bonds create the shapes and properties of, well, everything. So first stop, the mystery of attraction. I mean, atoms have these positively charged centers that should be pushing each other apart, right? So how in the world do they end up sticking together at all? Well, it really all comes down to this epic tug of war. You've got the positive nucleus of one atom pulling on the negative electrons of another. That's the attraction. But at the same time, you've got the two positive nuclei pushing each other away, and their electron clouds are repelling each other too. A bond only forms if attraction wins this battle. And the star players in this fight? They're the outermost electrons, the ones we call valence electrons. Now, to figure out what makes a winning combo, one of the best tricks is to look at the exceptions. The elements that are famous for not bonding with anything. I'm talking about the noble gases. They hold the key to the whole puzzle. Okay, so just look at this chart. See that last column, valence electrons? Look at neon, argon, krypton. What do you see? 8, 8, 8. Aside from tiny little helium, every single one of these super stable, too cool to bond gases has exactly 8 electrons in its outer shell. That's not a coincidence, my friend. That's the magic number. And that beautiful pattern gives us our golden rule for all of chemistry, the octet rule. You can basically think of it as the ultimate goal for almost every atom. They will beg, borrow, or steal, or more accurately, give, take, or share electrons to get that perfect, stable set of 8. Now, trying to keep track of all those electrons can be a real headache. So chemists came up with this brilliantly simple shortcut. We just ignore all the inner electrons and focus only on the important ones, the valence electrons. We just use the element symbol and some dots to represent them. It's called a Lewis dot structure, and it makes everything so much easier to see.
So, if the goal is to get to 8 valence electrons, what's the most direct route? Well, for some atoms, it's just a simple transaction, a little give and take. And this strategy creates our first major type of chemical bond.
We call this an ionic bond, and the keyword here, the keyword, is transfer. You have a metal atom with, say, 1 extra electron, and it just completely gives it away to a non-metal atom that needs one. This creates these charged particles, called ions, and because opposites attract, they stick together like tiny, powerful magnets. And the poster child for this is table salt, NaCl. Sodium has this one lonely valence electron it is just dying to get rid of. Chlorine, on the other hand, has 7. It is so close to a perfect octet. So, sodium happily hands over its electron to chlorine. Now sodium is a positive ion, chlorine is a negative ion, and bam! That powerful attraction between them locks them into a super strong ionic bond. Okay, but what happens when you have 2 atoms that both want electrons? Neither one is just going to give an electron away. What do you do then? Well, if you can't beat them, you join them. They have to learn to cooperate. And that brings us to our second major bond type, the covalent bond. Instead of a transfer, the atoms share electrons. It's like they create a shared pool of electrons that circles both of them. And this way, each atom gets to count those shared electrons toward its own octet. It's a total win-win. For example, take 2 fluorine atoms. They each have 7 valence electrons. They each put 1 electron into the pot, forming a shared pair. And just like that, they both get their stable octet. Oxygen needs 2 electrons, so 2 oxygen atoms will share 2 pairs, forming what we call a double bond. And nitrogen, it needs 3, so it forms an incredibly strong triple bond by sharing 3 pairs of electrons. Okay, so we've got give and take ionic bonds, and sharing is caring covalent bonds. But so what? How does this actually play out in the real world? How does the bond type determine what a substance is actually like? Oh, it makes all the difference. Just look at this comparison. Ionic salts versus covalent ethane. Salt is a solid that melts at a scorching 801 degrees Celsius. Ethane is a gas that melts at a frigid -183. That's a massive difference. The powerful attractions in ionic compounds make them hard solids with high melting points, while the weaker forces between covalent molecules usually make them gases or liquids. This stuff isn't abstract, it defines our physical world. And it doesn't just stop there. Bonding also defines a molecule's 3D shape. There's this theory with a ridiculously long name, valence shell electron pair repulsion theory, or VSEPR for short. But the idea behind it is actually beautiful and simple. It just says that electron pairs are clouds of negative charge, and they all repel each other. So they're always trying to get as far away from each other as possible. And this simple rule of repulsion creates predictable shapes. If you've got 2 electron pairs around a central atom, they'll push to opposite sides, making a straight line. 3 pairs, they'll form a flat triangle. And 4 pairs will spread out into a 3D shape called a tetrahedron. It's really just geometry. In a perfect tetrahedron, like you see in methane, the angle between any 2 bonds is exactly 109.5 degrees. That is the absolute maximum separation you can get for 4 things around a central point. It's just pure math. But, and this is a huge but, here's the twist. What happens when some of those electron pairs aren't actually part of a bond? They're just lone pairs hanging out on the central atom. Well, because they're not stretched out between 2 atoms, they're bigger and puffier, and they act like bullies, pushing the other bonding pairs closer together. A perfect example is ammonia. It's got 4 electron pairs, so you'd expect that perfect 109.5 degree angle, but one is a lone pair. Its extra repulsion squishes the other bonds down to 107 degrees. And water is even crazier. It has 2 of these lone pair bullies. They push the bonding pairs way down, creating an angle of just 104.5 degrees. This is the entire reason water has its famous bent shape. It's all because of those bossy lone pairs. Okay, let's zoom back out. We started with a simple question, why H2O? And we've uncovered this incredibly elegant set of rules that governs how our world is built. It all comes back to the octet rule. That simple, fundamental drive for an atom to get a stable set of 8 outer electrons is the engine that drives chemistry. Whether it's the all-or-nothing transfer of an ionic bond or the cooperative sharing of a covalent one, it's all about reaching that stable, noble gas-like state. From there, the simple geometry of repulsion gives molecules their unique shapes, and those shapes determine their properties. It's pretty amazing, right? A few simple rules give rise to the infinite complexity of the material world. And that leaves you with one last question to chew on. If all of this can be built on such simple principles, what other complex, beautiful things in the universe are just waiting to be understood through a similarly elegant code?